In this lesson on moments, I want to focus on tilting and things that are tilting. So here I've got a car park barrier. Okay, now this is quite a kind of logical use of moments here. So I've got this big rod here which reaches across the car park, and there's a little support at the very end. There's a support here, and then we've also got this really big weight at the end. So at the moment it's sat there in equilibrium, but if I came along and I pushed on this handle and I pushed downwards on it, then I could open the gate. And that is what we would call tilting. We would say that it's on the point of tilting around here when you apply just enough force to make it start lifting off. Now when it's just about to lift off from this one here, the support at this far end would obviously be 0, because it's not actually helping support it at all, because it's just about to lift off from it. Okay. Now what I want you to do, I've put in some details here of how I'm going to model this situation. And I want you to answer certainly part A, and then we'll do part B together. But I'll obviously go through A as well in a minute. So take a bit of time to use the details I've used there to model this situation, and then have a go at part A, and then we'll talk about B in a minute. Okay, so I've got my diagram here. So this C here, this is this bit here. B, this is the little support at the very end here. And then A, this is this big weight here. Okay. And I've put the dimensions on as well. Now I've got reaction force at C, I've called it, which is this support here. And I've got a reaction force here at the far end, which is B. Now notice as well that the force B at the very end is right at the end. There's no gap here. Okay. So let's do what we normally do. Let's resolve vertically. So I could say that RC plus RB equals 4G plus 3G, or obviously that's 7G. Now what I'm going to do is I'm going to take moments about a point. I'm going to do moments about point C. The reason for that is then I don't have to worry about RC, because that's distance 0 away. So I'm taking moments about here. Okay. So if I do that, I've got 4G times 0.7. So that's this moment here. That's trying to make it rotate this way, so anti-clockwise. This force here, RB, that's also actually trying to make it go anti-clockwise. Sometimes people don't spot that because they look like they're going opposite directions, but one's on the left of the pivot, one's on the right of the pivot. So this is making it go anti-clockwise, but also RB is making it go anti-clockwise too. So this is going to be plus RB times, this distance here would be 3.3 meters from this red dot all the way to RB. That must be equal and opposite to 3G, so this one here, that's making it go clockwise, times 1.3 meters. Okay. Now I can solve that equation to get RB, which is 49 over 15 if we want it exact, or that's about 3.3 newtons. And then I can substitute that into the equation up here, the first one we wrote, to get RC, which is 196 over 3, or 65.3 newtons. Okay, there we are. Now for the second part, what extra force has got to be applied to the leftmost point? So basically, if I came along and pushed down on this like this to open a barrier, what force have I got to apply to make it start to open? Okay. Now, when it starts to open, like I spoke about before, this support is no longer going to do anything, so it's going to lift off of this point here. So RB is going to become 0. Okay, so this isn't actually providing any support, so this is just going to become 0. Okay, when we do the second part. So now what I can do is I can do moments about C. C is probably the most obvious point to use for moments here because that is physically the point that it is rotating around, so it's easier to imagine in your head. So if I take moments about C, I've got 4G times 0.7 still, so I've still got this big weight here. And then I've also got plus the extra force I'm going to apply, so I'm going to push down on it with force F, let's say. So that's what's going to be plus force F times 0.7. Now remember, this reaction force isn't here, so that doesn't affect it in any way. So that's got to be equal and opposite to 3G times 1.3. Okay. Now obviously if it is actually opening, then it won't be equal and opposite. It will be these two forces are bigger than the force on the right. But if we just want the point where it starts to tilt, or the point where it starts to lift off from B, then we can set them equal. And this is then an equation I can solve. And I get F equals 15.4 newtons. That would be the force I'd have to push down on it with to make it start lifting off. Obviously, anything more than that, this is then going to become bigger than this force, and then it will start to actually lift off completely. Okay, so that's the sort of thing we're going to look at, is on the point of tilting. So in this example, we've got a uniform beam. So it's uniform, so the mass is exactly halfway along it. I'm not sure this is quite drawn to scale, this one, but we'll draw it halfway there. Of mass 45, so the weight is 45g. Rests horizontally and supports C and D, where A to C is 5 meters, C to D is 9, and then this bit is 2. When a child stands at A, so we've got an object on point A here, the beam is on the point of tilting about C. Okay, so that's kind of what's different here, is it's on the point of tilting about C. So we've got this weight here, and we've got to find the mass of the child. So I'm going to just label this as mg. We've got to find out what m is. If it's on the point of rotating about C, that means that C is your pivot, and it is lifting off here. Okay. And because it's lifting off there, that means that RD is 0. It's not actually supporting it anymore. Okay. And obviously you've still got a value of RC here. So to find the mass of the child, the easiest thing to do is to probably just take moments about C, because that is physically where it is pivoting around. So that's the easiest place to take moments about. So we've got mg times 5 over here, and that is a anti-clockwise moment. That is equal and opposite to, now RD is 0, so we don't need to worry about that because it's lifting off. But that's equal and opposite to 45g times this distance here, where it's a uniform plank of 16 meters. So it's going to be 8 meters along, so this bit must be 3. So times 3. Okay, and we can just write that. Now, you might say, well, if it's on the point of tilting, is it in equilibrium? Well, because it's on the point of tilting, it is still just in equilibrium. It's a bit like with friction, where it's on the point of sliding. It's just about to start rotating. Okay, so you can still use this idea of it being in equilibrium. The main difference is that this support is no longer actually supporting it. And if we solve this, we then get m equals 27 kilograms as the weight of the child. So in this example, we've got a slightly different kind of context. Rather than a plank on some supports, we've got a rod, which is non-uniform, and this time it's suspended from a pair of cables. Okay, so we've basically got a long plank, and it's strung up to the ceiling by these 2 cables. The rod is called AB, so I'm just going to label that. The length overall is 10 meters, and the weight is 40, and it's non-uniform, so I'm just going to put it somewhere that's not halfway. We'll put it about there. Okay, so the weight is 40 newtons, and it's suspended from these 2 cables, so that must mean that there's a tension here, and there's a tension here. They're not necessarily the same, so these are points C and D, so I'm going to call this TC and TD. Okay, so we've got this plank which is strung up by 2 cables. Now, we've got some other measurements as well. It says A to C is 3, so this distance here is 3 meters, and B to D is 2 meters. Okay. When a weight of 25 newtons is hung from A, so we're putting a weight here, which obviously got a force downwards of 25 newtons. When we do that, it's on the point of rotating. So if I pull down here, it's going to rotate about this point here. So this end here is kind of going to rotate upwards like that into the air. Okay, a bit like a kind of a drawbridge kind of idea. It's going to rotate like that. This end is going to lift up. So there's going to be still some tension here, and it's rotating about this point. But this string here, if this end moves up, this string is basically going to go slack. And because it's slack, we can say that this is going to be 0. There's no tension in that string anymore. Okay. And that's just because it's on the point of rotating. Okay. Find the distance of the center of mass from A. So we've got to find, let's just mark it on there. We've got to find this distance here. okay, to the 40. So we will do moments about C, because that is where it is physically pivoting around. So we've got 25 newtons times a distance of 3, and that is trying to make it turn anti-clockwise. Trying to stop it, we've got the 40 newtons here. And the distance away from the pivot is this distance here. So that would be distance x minus 3. TD we don't have to take into account because the string's gone slack, because it's rotating. There's no tension in this bit here. So we don't need to worry about that one. And this is then an equation I can solve. And I get x equals 4.875 meters. Let's just check, does that make sense in terms of my diagram? Well, this is 3 meters here. And then up to here, that would take me up to 8 meters. So yeah, around here somewhere seems sensible. Okay, here's 2 more for you to have a go at. I'm going to try and fit both of them on the screen so you can pause it and have a go at both of them. Okay, and then I'll go through each one. So for this first one, so a uniform plank of mass 100 kilograms. Let's just put the weight on there. So that's 100 G. And obviously the distance is uniform this time. So the overall length is 10, so this is 5 meters. So that bit's 2. And then this bit is 3. Okay. A man of mass 80 kilograms starts walking from one end of the plank A to the other end. Find the distance he can walk past B. So we're looking for how far can you walk past point B. So maybe he's there before the plank starts to tip. Okay, and his weight was 80 G. So basically, if he walks too far this way, it's going to start to rotate about point B, and this end of the stick will sort of come upwards like this. So let's take moments about point B, where I've done this big blue blob here. So I've got 80 G times distance, let's just call it X, that's what we're trying to find. And that equals 100 G times this distance here, which is 2. And I can solve that, and I get X equals 2.5 meters. So that's the distance beyond point B. So for the second one, let's just start by drawing out a diagram for it. So we've got a uniform rod of length 5 meters and weight 20, so the weight is going to be exactly half weight. This is AB. The rod is resting at supports C and D, where A to C is 2 meters. Let's put C here. This distance is 2 meters. And then we've got another support D here, where the distance here is 1 meter. Find the magnitude of the reactions at C and D. So we've got RC and RD. Let's just put some other measurements on. This is exactly halfway, and the overall length is 5. So, okay, I haven't drawn this very well to scale, have I? But that's 0.5 meters in there. So let's resolve vertically. So vertically, I've got RC plus RD equals 20. And if I take moments about a point, I'm going to go for moments about C, so about this point here. So I'd have 20 times 0.5. That must be the same as RD times, well, the whole thing's length 5 minus this 2 minus this 1. So this gap here must be 2. Solve that to find RD, which is 5 newtons. So then that means that RC, using this first equation, must be 15 newtons. There we go, that's our first part done. Okay, now let's look at the second part. Maybe we'll just do it in a different colour on the same diagram. A particle of weight 12 newtons is placed on the rod at point A. Like that. Show that this causes the rod to tilt about the point C. So let's take moments about C, just like I did in the last one. So we've now got 12 times 2, And then we've also got, so that is trying to make it rotate anti-clockwise. The other thing that's making it try and rotate anti-clockwise is RD. That's trying to make it do the same thing. So plus RD times 2. That's how far away it is from C. Now, if it was in equilibrium, and we're basically going to show that it's not in equilibrium, so that it's tilting. Now, if it was, though, this would be equal and opposite to the center of mass, the weight, 20 newtons times 0.5. Okay. Now, if I solve this equation to find RD, you will find that RD is negative 7 newtons. Now, that's obviously not possible, but what this is saying is that to keep it in equilibrium, RD would have to push down with 7 newtons. Okay, so basically this is not possible, so it must be rotating. So I'd probably just write not possible. So RD is just going to be 0, which implies that it's tilting. Okay, because what this minus 7 means is that actually it would need to push down to keep it in equilibrium, because we've assumed that it is in equilibrium here. Another way you could do it is you could look at maybe the total moments, but I suppose you don't know what RD is necessarily, so this is probably the easiest way to do it actually. Okay, for the last part, it says a second particle of weight 100 is placed on the rod at point E, which we don't really know where it is, to hold it in equilibrium, so to stop it tilting. Find the minimum and maximum distances of E from A. So basically we're going to add in another object, I'll do this in a different colour, to keep it from tilting. So at the moment when I put this here, this end is going to lift up. So I could put an object maybe here to keep it balanced. And that would, if I put it in the right kind of position, that would weigh this end down so it stays in equilibrium. And this would be the minimum distance. Okay, so that's my first case, and the distance from A, if I label it as x1. Okay, and then my other one, I could put it so far to the other end, maybe down here somewhere, that actually it starts to tilt about D instead. So this end actually starts to lift up, and that would be the furthest I could put it away. So I'm going to call that distance x2. Okay, let's put that on here. So those are my two sort of different cases. Now, obviously, remember these are not being applied at the same time. These are two different cases. And the weight was 100. Just put that on for both of them. Okay. So let's look at both of those cases. Let's do x1 first of all. So this is going to be the minimum distance. Okay. And when I put it here, it's still going to be on the point of tilting about C, but this is just about enough to keep it flat or to keep it horizontal. Okay, so tilting about C. So I'm going to take moments about C. And when I do that, I've got 12 times 2 still, and that's trying to make it go anti-clockwise. And then against that, I've now got the weight, 20. So I've got 20 times 0.5, but now I've also got this extra weight of 100 times distance. Well, I've written this as x1, but from C, that's going to be x1 minus 2 meters for this gap in here. Okay, and I don't have to worry about RD because I've said it's on the point of tilting about C. So RD is still 0 because I'm looking for the minimum distance to keep it just so it's on the point where it would lift off. Right, so this equation here, I can solve this to find x1, and you'll get x1 is 2.14 meters. So that is 2.14 meters from A, so a little bit past the pivot, which makes sense. Now let's look at the second case, so x2. Now x2, I've put it so far to the right that actually it's going to start to tilt about D, and this far end here, A, is going to start to lift up. So RC would be 0. Okay. So I'm just going to make a note of that here. So this point is tilting about D. So I'm going to take my moments about point D. So I've got, let's deal with 100 first. I've got 100 times, now the distance from D, this little distance here, that is going to be x2. So that'd be the distance, basically the entire length from A up to here. then we're going to minus from A up to D, which is 4 meters. So that's x2 minus 4. And then that is equal and opposite to the other forces, helping it go the other way. So that's 20 newtons times this distance here. This distance here would be 1.5. And then we've also got the 12 newtons here as well. So that's 12 times, that's 4 meters away. And I can solve this equation to get x2 is equal to 4.78 meters. Okay, so those are my minimum and maximum distances where I can place this. Okay, so questions for you to do. Have a look at exercise 4E, which is focusing on things that are tilting. Maybe just pick out a selection of questions from there. And you could actually have a look at the mixed exercise 4 as well and pick out some of the exam style questions from there would be good as well. There's a little bit more content in this chapter still because it overlaps with chapter 7 a little bit, but we've done all the content for chapter 4 itself. And our next lesson, we're going to look at the content where it overlaps with chapter 7. So that's things like ladders and things like that.